The wind rarely blows directly along the line of an en route track or along the centre line of a runway. There is almost always an angle between the track or the runway direction and the direction from which the wind is blowing. However, in this case, where the wind is blowing at an angle off of 40 degrees from the left, only part of the force is directed along the runway. The other part is directed across the runway from left to right. The wind velocity is resolved into two components. One acting along the runway, called the headwind component, and the other acting across the runway, called the crosswind component. Let's assume that the wind strength is 20 knots. It would be possible to solve this by taking the sine and cosine of the wind angle of 40 degrees. The headwind component will be 20 knots times the cosine of 40 degrees, which is 15 knots, whilst the crosswind component will be 20 knots times the sine of 40 degrees, which is 13 knots. However, it is simpler to do it using the navigation computer. In dealing with the wind, we first need to be sure whether the wind direction has been given in true or magnetic. The rules are easy to understand. Any forecast wind is given in true direction. Thus, any written meteorological information, for instance a TAF, METAR or VOLMET, will be in true. Forecast winds are used for planning navigation as well as for landing, and navigation tracks are normally initially measured in true. Any information used to help the pilot line the aircraft up on the runway will be given in magnetic, because runway directions are always magnetic. Thus, a wind from an air traffic controller will be magnetic, and the ATIS always quotes magnetic wind direction. To summarize, magnetic, ATC and ATIS, true, VOLMET, TAF and METAR. The squared section at the bottom of the slow-speed slide allows us to find the head and crosswind components of a known surface wind for the runway we intend to use for takeoff or landing. The scale here is identical vertically and horizontally. Position the slide with the zero speed line under the center circle. Align the surface wind direction with the index mark. Put the wind mark the appropriate distance on the slide center line below the center circle to represent the wind speed. Move the rotating scale to bring the runway direction under the index. Measuring vertically from the zero speed line to the wind mark gives us the headwind component. As you can see, it is 15 knots, as it was when we used the calculator. Measuring from the center line horizontally to the wind mark tells us both the strength of the crosswind component and whether it's coming from the left or the right. In this case, it is 13 knots, again as it was from the calculator. Once again, an example will allow you to see the method used more clearly. You have been allocated runway 36. The surface wind is 040 at 20 knots. What is the headwind and crosswind? Position the slide with the zero speed line under the center circle. Align the surface wind direction of 040 degrees with the index mark. Put the wind mark on the 20 knots point below the center circle on the slide center line. Move the rotating scale to bring 360, the runway direction, under the index. On our rotating scale, this is marked as 0. Measuring vertically from the top line to the wind mark gives us the headwind component of 15 knots. Measuring from the center line horizontally to the wind mark gives us the crosswind component of 13 knots and the direction from right to left. Sometimes the wind is blowing from a known direction, but it is gusting. A gust is defined as a change of 10 knots wind over a period of 1 minute. However, gusts are often stronger and change more rapidly than this. You may wish to try to land between gusts. In this case, you continue the approach down to the point at which you must commit to a landing or go around. For a visual approach, this will be far lower than an instrument decision height. It may be 50 feet or lower, depending on the handling of your aircraft. At the last moment, you request a spot readout of wind from the tower. If the wind strength from the actual direction gives a crosswind component of your crosswind limit or less, you can land. Otherwise, you must go around. The moment of visual committal decision is no time to start calculating crosswind limits. You should have thought about it beforehand. Before you start the approach, you calculate what wind strength from the forecast direction corresponds to your crosswind limit on the runway in use. The calculations are made at the top of descent, to allow an instant decision at the visual committal point. Take the following case. The TAF wind velocity is 180, 10 gusting 50. The variation is 15 west. Runway 23 is in use, and the crosswind limit is 25 knots. This type of calculation requires a different technique. In this case, you do not have a single value of wind, so you cannot put it on your navigation computer. Instead, you put the runway and the crosswind limit on your computer, like this. Put the runway QDM of 230 up at the top. Then draw in 25-knot crosswind limit parallel lines, either side of the center line. Now rotate the wind disk to the direction that the wind is coming from. Don't forget to apply variation if necessary. In this example, the wind comes from a TAF, which is true direction. So the magnetic direction will be 195 degrees. Now note where the applicable crosswind limit line crosses the center line. In this case, it is at 43 knots. What this is telling you is that when the wind from 195 magnetic reaches 43 knots, it will give you 25 knots crosswind on runway 23. Provided that the wind is less than 43 knots from 195 magnetic, you may land. On occasions, you can be limited by both crosswind and headwind. You might have to land a heavy aircraft onto a single runway airport, and that runway might be short. In this case, you may be on your landing distance available performance limits, and may need, say, at least 10 knots down the runway to land. At the same time, there is a crosswind. Take this example. Runway 35. Air traffic gives the wind velocity as 030, 10 gusting 40. Because of your weight and the runway length, your minimum acceptable headwind is 10 knots. The crosswind limit is 20 knots. As before, draw in the 20-knot crosswind parallel markers for runway 35. But this time, in addition, draw in a 10-knot headwind limit line. We'll shade the graphic, just to make it obvious which is the usable area. You would not do this in practice. The answer has to lie in the unshaded area. Now rotate to the direction that the wind will be coming from. In this case, 030 magnetic. Note where the unshaded area intersects the center line, at 11 knots and 31 knots. What this is telling you is that when landing on runway 35, If the wind from 030 degrees magnetic is less than 11 knots, you have less than 10 knots headwind down the runway. You cannot land. If the wind is any greater than 31 knots from 030 degrees magnetic, you have more than 20 knots of crosswind component. You cannot land. If the wind is between 11 and 31 knots from 030 degrees magnetic, you have 10 knots or more of headwind component, and you have 20 knots or less of crosswind component. You can land. In general, you should avoid landing with a tailwind. If you are given a runway with a tailwind component, ask air traffic control if you can use the other end. However, you may occasionally have questions that involve tailwind components, so you should know how to deal with them. The first thing to notice is that you cannot directly plot the horizontal line representing a tailwind component in the normal way, because it is above the horizontal scale line. You are in the curved part of the wind slide. Let's take a worked example. The runway is 09. The variation is 10 east. And the ATIS gives the wind as 320, 10 gusting 30. Your maximum tailwind component for this particular landing is 10 knots. What is the maximum wind speed from the given direction that you can accept? ATIS is given in magnetic direction, so the value of variation is unnecessary information. Ignore it. Watch out for this trap. Bring the runway direction, 09 in this case, round to the top. Now move the speed slide to bring 10 knots under the centre dot. Draw in the tailwind component limit line. Then, most importantly, don't forget to move the speed slide back to put 0 under the centre circle. Now rotate round to the wind direction. Read off the value of the intersection. In this example, it is 16 knots. If you find all that too complicated, don't forget that you can always treat it as a headwind problem on the reciprocal runway. Try treating it as the same type of problem as shown in the scene before last. With the same wind, 320, 10 gusting 30, as in the last example, but this time landing on runway 27. You get the same answer, 16 knots. Another problem sometimes arises, which is quickly solved on the computer. Between what directions can a wind of given speed blow without exceeding a stated crosswind component? For example, it is required to find the directions between which a wind of 50 knots may blow without creating a crosswind component of more than 30 knots on a runway of direction 250 degrees magnetic. With the runway direction set against the true index, mark a cross on the centre vertical line to represent the wind speed of 50 knots. Turn the plastic disc clockwise until the cross indicates a crosswind of 30 knots. Note the direction which now appears against the true index, which is 214 in this example. This tells us that the maximum off-runway direction for this wind speed and crosswind limit is 36 degrees. So, if the wind comes round to the left, we should reach the same limit at 286 degrees. Turn the plastic disc anti-clockwise and repeat the procedure, reading off the direction which appears against the true index. It turns out to be 286. This completes the lesson on using the navigation computer to solve wind component problems.